Hello. Before I introduce Theoden Brown, I want to introduce their outside evaluator, Dr. Glenn Wiley. Dr. Wiley is the director of the Rocco Ortenzio Neuroimaging Center at the Kessler Foundation. He's also a professor in the Physical Medicine and Rehabilitation Department at Rutgers, New Jersey Medical School. Dr. Wiley's research interests fall into three broad categories: cognitive control, cognitive fatigue, and the neurophysiological effects of cognitive interventions. It's this part of his research that made him the perfect outside evaluator. In fact, in Dr. Wiley's work investigating the neurophysiological effects of cognitive intervention, he's investigated functional changes in the brain associated with interventions such as exercise and interventions designed to improve memory. In order to better understand these processes, he's employed several of the tools of cognitive neuroscience, including functional resonance imagery, fMRI, event-related potentials, ERPs, functional near-infrared spectroscopy, and position emission tomography. We both greatly thank Dr. Wiley for being Theoden's outside evaluator, and we thank Dr. Wiley's team for the support given to Theoden throughout this exhibition. And now, to introduce Theoden. While Theoden will focus on the work that they did during their exhibition, I want to point out that they began poking at the edges of this question in their 9th grade year, when we acquired the components of an EEG and were audacious enough to believe that we could cobble together a functioning 8-channel device to measure brain activity. Through each iteration and each new thing we learned, Theoden was there, asking questions, offering insights, making modifications, supporting others, and quite frankly, doing the work. What you're about to see is the culmination of an exhibition, but really, it's the culmination of 4 years of inquiry. And so, without further ado, I give you Theoden and their exhibition, Monitoring Musically Modified Memorization and Electroencephalographic Experience. Theoden.
Hello, I'm Theoden, and I have a question for all of you. What is science? Tell me.
Discover. Questions.
Exploration of the world. Trying to know.
Testing. Data. Process.
The search for truth.
Experimentation.
A word.
All good things, all good things. Very true. So now that we have sort of a working definition of science, I'll talk a little bit about a scientist. So the Oxford English Dictionary essentially describes a scientist as a person who does science. But I disagree. A scientist cannot truly be described as a person who does science.
What is a scientist?
Well, Gabriel, it might take a bit to answer that question. So I'm going to tell you a story. Way back when, 4 years ago, Anne-Marie ran this group project about neuroscience. So we learned about the anatomy of brains, we learned a little bit about experimental design, and we put together this device that measures your brainwaves. It's called an electroencephalogram, or EEG for short, and it uses these little pieces of metal to measure positive and negative charges on your scalp. And of course, we decided the best way to secure these electrodes was by taping them to this baseball cap. So with this magical brainwave reading baseball cap, we looked at my brainwaves while playing instruments, we looked at our brainwaves while listening to music, we tried to make a lie detector while Anne-Marie wasn't looking, all the good stuff. So no real plan or experimental design, really just messing around with our makeshift EEG. Later that year, Hillary did an exhibition, and part of that was that she put the EEG electrodes into a very nice 3D printed frame, which allowed us to easily measure the exact same spots on the brain every time we were collecting data. This was very important. Hillary also started doing the scientific method and doing experiments rather than just messing around. Also a very important step. So here I was as a sophomore, looking at brains while people listened to music, and I was trying to find a way to make sense of all this data I was collecting. So I decided to look at the frequency of brainwaves, organizing them from fast to slow, alpha waves, beta waves, theta waves, etc. In further experiments, I decided to compare the amplitude of waves. But in the end, I found these approaches to be rather sophomoric. So in junior year, I decided I am going to do something more real. I am going to look for patterns. So I went around and I circled a bunch of these patterns, which I thought, these are obviously related. They look the same. And so I was like, yes, this is the way to analyze data. This brings me to my exhibition, where I did some neuroscience that would make my previous experiments look like a high schooler bumbling around with a machine they didn't quite understand. So let me tell you a bit about why I'm doing this experiment about monitoring musically modified memorization. A long time ago in elementary school, I found that I listened to music while I was working, and it helped me learn the things that I was doing, and it was all great. Now, the problem was that we weren't allowed to listen to music during class time, even if it was individual work. So I asked my teachers, why can't we listen to music while we're doing work? And after giving some unhinged response about people cheating on tests, they told me studies actually show that music in a classroom setting is distracting, and it decreases your memory accuracy, and it's just not good for your learning. So I went home and I did some research, and I found there are studies saying all of this. Now, the thing is, there's an equally numerous amount of studies that show that listening to music is calming, and it increases the accuracy of your memory, and it increases your focus in a classroom setting. So there's a lot of conflict about what music actually does for our learning. So one of my favorite studies on this topic was conducted by Year and Wren. It bears the rather wonderful title, Visual Sequence Encoding is Modulated by Music Schematic Structure and Familiarity. So this shows that specifically the type of music that helps people learn is music which has a similar texture throughout and is familiar to the person listening to it. So freshman me would look at this and think, well, this is great, let's just run a similar experiment with an EEG, and then we can compare all of the results to each other, and then we can look at the data, and then we'll know exactly what's going on in the brain, and then I can show my elementary teachers my brainwave findings and prove them wrong. But that's not really how to think like a scientist. So now I look at all of this sort of conflict in the scientific world, people saying this, people saying we found this, and the way to think like a scientist about this issue is to say, well, we have this EEG. It's a tool that can actually sort of get to the root of the issue, and it can give us an insight into what's going on in your brains, so we'd better ask questions that are more concerned with the truth than right or wrong. So I refined my question. Now I'm wondering, how does music change the way our brain encodes and recalls verbal and visual stimuli? Very specific question that allows us to peer with this EEG into a very specific part of our minds. So the way that I decided to go about answering this question was with a three-phase experimental design. The first phase was familiarizing participants with a specific piece of music to ensure that they were familiar with it, and also showing them a series of words that was basically teaching them how to do this experiment. Phase one, no data collected here. Phase two is where the data collection actually starts. So this is where participants memorized a series of visual stimuli that looked sort of like this, just a bunch of words. And half of these words they memorized while listening to music. Half of these words they memorized in silence. This brings us to the third phase, which happens about 24 hours later. In this phase, participants are presented with some words they saw before and some words that they had never seen before, or at least had never seen in this setting. So they essentially had to just pick the 5 words of this multiple choice quiz, which they had seen before. Now, similar to phase 2, half of the words were accompanied with music, and half of the words were in silence. Now, the data that I get from all of this, after doing all of this and having all of this EEG data, it starts to look like this, and it comes out looking like this, and it comes out looking like this, and there's all these funny shapes everywhere, and it's quite hard to make sense of it. So this brings us to interpreting data. Despite all of these funny looking lines and funny looking graphs and charts, what really is the data that I was collecting are numbers like these. Millions of these numbers, hundreds of thousands of rows of numbers, lots of numbers. Now, these numbers are all positive and negative charges collected from specific areas on your scalp, which are above different areas of the brain. Now, these numbers are the truth, in a way. And even though they've sort of been processed and compared to each other in sort of weird, wacky ways, they do represent what is actually going on in our brain. The problem is interpreting these numbers can be wildly difficult. You can't look at this and understand what's going on. Nobody can, none of us can. So this brings us to our data analysis. So the way that I analyzed all of this was through event-related potentials. This is the section of data which is about 2 seconds long, which occurs right after a participant of this experiment is shown a visual stimulus or right after they respond to one. So essentially, this is the part of the data that we really care about. Now, it's very spiky, and it's hard to understand. So the first thing to do with this data is to get rid of all of the noise, to only focus on the things that actually matter. So what I do is I create a quadratic regression of it, and it smooths out the data, getting rid of all of the spikes, which are just high-frequency brain waves that we don't care about, and electrical noise. Now, we wind up with these ERPs. So these ERPs have a number of ways of being looked at. You can look at the overall shape. You can look at whether it starts in a more negative area or a positive area. But one helpful way of looking at this is through positive and negative peaks. You can label all of the peaks as this is like the first negative peak, the second negative peak, or the sixth positive peak, or what have you. Now, the problem with analyzing these ERPs by doing this is that I have 120 event-related potentials per test subject. Now, that's a lot of data to go through. So how do we interpret this huge amount of data? Well, there's some techniques called layering and averaging, which are particularly helpful for this. This is an image of 5 event-related potentials stacked on top of each other. Now, you can see a general trend that's happening because we've layered them on top of each other. You can see what's similar about all of them. You can see there's this sort of area of negative space under the wave. You can see that where there's more positive charge and where there's more negative charge. And that is a decent way of looking at the data. But an even better way of looking at this is by creating a trend line. This can either be done by putting all of the data up here and creating a regression, or by averaging. I choose to average the data. This creates a nice representation of what's actually going on across multiple different ERPs. What this does is it enhances the shape that is actually related to the heart of the ERP. What I mean is that if, say, this ERP was taken from when a participant said a word while they were listening to music, then you can see that what is similar about all of these ERPs, what's put together, it creates a more comprehensive sort of average of what is actually going on during those specific circumstances. What this also does is averaging the data reduces noise. It gets rid of the things that we don't care about. By throwing more and more ERPs into this averaging, noise, extra things we don't care about, things that the brain is doing that's not correlated or caused by the task at hand are sifted out of the data. And we're left with this wonderful line, which actually represents what is going on in the brain when you do a task in general. Now, that's just one electrode. We were measuring 8 different spots on the brain. Here's all of the electrodes stacked on top of each other. Sometimes this is helpful in the same way that layering ERPs is helpful, but a lot of the times it's easier to look at these electrodes separated. So this is the form that my data will take. This whole process of ERP analysis is one of the things that really separates this experiment from my previous work. This ERP analysis is really going into the details of the numbers and going into the truth of the data to bring out the patterns that actually matter. And because of this sophisticated analysis, I'm actually able to use this to pursue truth and science. So, here are my results. I'll start with the memory accuracy data. Here are some test subjects, and here is the amount of answers that they got right with music and without music. Here are 2 test subjects which I was able to get a lot of data from. I'm going to show you the brainwaves of these subjects because I was actually able to get enough data from these to create meaningful event-related potential averages. So you can see music, all of the answers correct. With silence, 90% of the answers correct. Coincidentally, both test subjects performed the exact same in this memory test. So that's all stuff that doesn't really matter. What really matters is what's going on in the brain. Here is participant A. You can see on the left, this is their brain while encoding a word, while looking at a word and knowing that they have to memorize it. And on the left, it's with music. On the right, it's with silence. You can clearly see there's a difference between these waves. There's a large positive peak, which happens at about 1.5 seconds after seeing the word. Now, in the silence, this doesn't quite happen. There's some other patterns. There's a negative peak about a half second after seeing the stimulus in the silent ERP. But despite all of this, there is a difference. Here is in phase 3, the retrieval phase. There's also some differences here. They're less prominent, and there's a lot more similarities. But there's still a difference. Here is participant 2. There is quite a clear difference between these different event-related potentials. You can see that some of these are trending from positive to negative, and those are often opposite from what is happening in the music and in the silence. Now, these also look very similar. This is during the retrieval phase. Now, because these ERPs looked more similar in the recall phase than in the encoding phase, you could possibly hypothesize that the difference that music makes is only in encoding and not retrieval. It's possible, but it's possible there's just patterns here that we're not seeing due to analytical issues or just because we haven't gotten enough data. So really what all of this is saying is there is a difference. There is a difference when you listen to music and try to memorize something. And that's the key of this exhibition in terms of results, is that this difference exists. Now, it's a scientist's life work to understand what is going on in the brain and when we're listening to music and how it helps us learn and all of the little specifics of it and what parts of the brains are firing and how exactly all of that works. And the first step of that is saying there actually is a difference between these two scenarios. And that's really the important part. That's part of the truth of the science, is going in these small steps. So in terms of continuing the science, one of the possible continuations would be to get a lot more data. Another would be to run experiments that isolate just the encoding process or just the retrieval process. Some others could be to look at the brain through different ways, such as an fMRI. So the other day, I was like, hey, Glenn Wiley, can I run my EEG experiments in your fMRI? And Glenn Wiley was like, yes, you can do this, which is quite frankly a crazy thing to say. People don't just let you use their fMRIs. They're incredibly expensive scientific instruments, and they're always in demand, and it's just an incredible opportunity to be able to use this fMRI. So thank you so much, Glenn, for allowing me to work with you there. I appreciate it more than I can say. So this is an image of my brain that Glenn Wiley helped me procure. Now, it doesn't actually say anything. It takes a long time to understand these results, but this is the first step in the process of uncovering more data. EEGs tell you when things happen in the brain. fMRIs tell you where. So, that being said, also, thank you to Brian Yao for showing me how he was able to run an EEG inside of an fMRI. That was one of the things I got to look at there, and it's an insane thing to put an EEG inside of an fMRI and not have it fly apart into a million pieces and not have it be damaging, and to be able to filter out that noise is quite incredible. I would also like to thank Anne-Marie for being an incredible sponsor. Thank you for always being there to discuss experimental design and data analysis. Thank you for, on multiple times, getting up at 5 in the morning to do EEG experiments. It was wonderful. And thank you to my fellow creatures for just being there during the last few days and being there while I was doing this last bit of work on this presentation. Yes, Gabriel, you have something to say?
You never answered my question.
Oh, did I not?
What is a scientist?
All right, if you must. So, a scientist is a person who wants to observe the universe in its true and beautiful form. A scientist doesn't want to use science to achieve an end. A scientist doesn't want to necessarily prove anything. What a scientist wants to do is to discover, and a scientist wants to do all of what they can to create a tiny little grain of knowledge. A scientist understands that really what it's about is this pursuit of truth. And often these pursuits of truth end up in very small discoveries. That's the beauty of it, is that being a scientist is really an act of love. You have to really devote yourself to understanding and discovering and learning about just the tiniest little things. And when you put all of these tiny little things together that scientists have so lovingly pored over and thought about and experimented on, that is when you get science. Think of science like many little specks of human knowledge. Each speck of human knowledge lovingly crafted by a scientist. Each speck working together to create this mass of human truth. And it's beautiful. And it's science. Thank you. Questions? Don? Oh, so they built it out of materials that aren't going to be taken apart by the magnetic resonance of the fMRI, and they were, instead of using a 3D. No, it wasn't mine. It was a specific EEG. Instead of using a 3D printed frame like this, they used a gel cap. And so another thing that they did on the data analysis side was they found that the EEG signals are actually predictable and reproducible. So they were able to just subtract that from the fMRI readouts in order to cancel out the noise. Yeah. Felix?
So if I was gonna do this project, I would have just been like done the testing and I saw that like the results was there was like this memorization for music and there was this memorization without music. How does adding like the actual brain waves modify that data that we can easily like see and understand in the sense of like there's this difference in results of the memorization like if music versus without music.
Yes, good question. So being able to say music helps some people statistically memorize things or it doesn't is sort of good in its own right, but what I really care about from this sort of scientific perspective is understanding why. And that understanding of why, because there's such an arguing, because there's so many people saying so strongly music is bad for learning, and so many people saying so strongly music is great for learning, what we need to do in order to get to the truth of the matter is look at your brain, look at what's actually going on, and pursue what the differences are. And the truth of it is that some people will learn better while they're listening to music, and some people won't. And some people will listen to certain types of music and have a better experience than other types of music. And there's all of this, all of these things that change between humans. And that's why the EEG is so important, is that it allows us to actually understand what is really going on to make all of this happen. And it's those little nuggets of truth like this does make a difference. And then understanding when the difference happens. Is it encoding or is it recall? And then maybe using an fMRI to understand where, and then getting all of these little nuggets of truth and then putting that together into a large finding is what we need to do in order to understand what's really going on. Yeah. Michael?
Maybe a slight tangent, but I'm curious if your research, your brain science research, has affected your like conscious awareness of listening to music, playing music, and music that you might compose.
I think it has. I think mostly what I found compelling in terms of in terms of like thinking metacognitively about how I think about sound and music is that our ears are so close to the part of our brain that processes sound that we process it faster than all of our other senses. And I think that's that's something I find so compelling as a musician, and it often leads me to sort of think about I'm hearing this sound and I'm having this experience of it. And I think also the way that learning about the way that we project sound in our minds and the way that connects to other senses, and that sort of like mystery of how we actually how our neurons turn that into experience has really shaped how I think about hearing sounds and interpreting them as music. Grant?
There was another experiment where we were tying knots. And so my question is kind of twofold. The first part is, was that related to this? And the second part is, I assume that the experiments you did here were not the first iteration of what you ended up with for this exhibition. So I'm kind of curious what the process was for choosing what experiment was the best for your purpose.
Yeah. The knot tying was one of those things where I was like, okay, I want to look at something spatial going on, and I want to understand how music impacts spatial memorization. Now, I wanted to focus more on verbal memorization because there was one reason is because Year and Wren in their experiment had already created a very good sort of template in a way for me to follow in terms of how to create experimental design. I didn't copy them, but I was heavily inspired by their process. And also, I wanted to look at something which was more relevant to what elementary schoolers tend to do. Back to my original inspiration for asking this question. Yeah.
In your research, when you were playing music, what music did you use and what was your thought process behind it?
I used a string quintet that Dvorak wrote. I chose it because, again, Jürgen Wren's experiment had shown that music that followed a sort of predictable pattern was beneficial for learning. So I chose a piece that had a rather repeating melody that was easily recognizable and had a pretty consistent texture. I also wanted to choose a piece that people hadn't heard before, and that way I could control how familiar people were with the music. That way I could say all of the test subjects were sort of equally familiar with the music in this way. Phoenix?
Do you plan on continuing this experiment?
Yes, I do plan on continuing it. I'm not entirely sure how, but I'm sure I can find some people with an EEG, or maybe, Glenn Wiley has this fMRI, which maybe he'll let me use sometime in the future. So yes, I do plan on continuing this experiment, and I want to know so much more, and I want to know all of the details, and I want to have a comprehensive view of how music interacts with learning in our brain, but I think that might take a while. Glenn?
I'm wondering about the treatment of noise and how you decide what's signal and what's noise. What might or might not be contained in the micro ripples, and what noise might exist in the larger structures. And I'm wondering if you ran the EEG attached to, I don't know, a dead salmon or a grapefruit, and backed out anything that looked similar.
One of the things that sometimes you can do is attach the EEG just to nothing, to air, and run it. And oftentimes you'll see these electrical noise patterns. They're very spiky and very fast. And so those sort of high frequency things, I suppose you could analyze them, but all of the scientific stuff that I've read has suggested that smoothing out the data is the best way to decrease the electrical noise. And most of that high frequency stuff is a lot of electrical noise. It's partially due to the fact that we're not actually measuring the real electricity that's going on in your brain. We're actually comparing the electricity in your earlobe to the electricity on your scalp, because the earlobe is a rather neutral section, but it still has some fluctuation, which is partially what causes those electrical noise bits. Yeah.
Did you try any cooling?
Try any cooling?
Cooling with your sensors?
No, I didn't. Dan Rapid?
Do you think there's any difference? Do you think that lyrical music versus instrumental music would have any effect on the memorization process?
It entirely depends upon the person. Augie?
I noticed when you were showing the different people, that seemed like each individual person had like a similar pattern that would show up between the different experiments. Did you do like a large number of tests, and like that each person would always have a similar pattern like that? Do you know anything about that? Between the one with and without music, there were still a lot of similarities, but it was like it seemed like it was a different pattern for each.
Yeah, there wasn't a specific thing that was going on between people. What was really going on was that there was a difference in their brains between when they were listening to music and when they weren't, and those differences were not similar across test subjects.
What about like the general like pattern that each person has? Is that consistent? Like if someone like did one test and then did it like a while later, I mean, it might not be something that we're looking for, but like is that just like some characteristic of like sort of like fingerprint for that person?
Oh yeah, yes, that's sort of what the event-related potential is all about, is taking multiple instances of this person recognizing a word and then sort of shoving those all together to create an image of what their brain does overall when they're memorizing a word. Mary?
Are you interested at all in combining this with psychological research, for example, studying the impact of telling your subjects that music does help memorize?
Yes.
And see how that influences the results?
I've thought about it. I I haven't thought about it a lot, but one of the interesting things is that one of my test subjects said that they thought that the music was distracting them and that they were having a hard time memorizing and recalling things with the music going on. But in reality, they scored much higher on the music memorization test than the silent one. So there's definitely a lot of interesting stuff going on in that sort of psychological and experiential realm. And I think that that can be paired with this EEG analysis to create a fuller picture of what's actually going on. And a lot of the times, that's a nicer way of communicating things to people than explaining that there was a positive charge after 1.5 seconds of an ERP. It's helpful in that sense. Caroline?
Were any of your test subjects musicians, and did that impact? Did you find the impact of that?
I can't say whether or not it impacted it, but yes, my test subjects are musicians. One of the things about being a scientist here is that it's very hard to acquire a perfect, huge group of test subjects. So the test subjects that simply had the time to participate in the experiment were a mix of people who were musicians and a mix of people who weren't musicians. Yeah.